Now, when we see the price of a call or a price of a put, we need to have this N function here, ND1, ND2. So what exactly is an N function here? So you see that also for a put, you have N minus D2 and N minus D1. So this N function is really basically the area under uh, uh, the probability density function of a normal distribution. So it's really the cumulative probability as of a particular point. So under a normal distribution here, a probability density function of a normal distribution. So is an if you integrate the density function of a normal distribution from minus infinity to a particular point, you get an area under this curve here. So that's where what the N function is. And whatever's inside the integral is basically this probability density function. Now, so now we know what the N function is. We can easily put in the Excel spreadsheet and to allow us to calculate the price of a call or the price of a put for a stock that does not pay any dividend under the Black-Scholes Merton framework. So you need 5 parameters. Actually, sorry, without the dividend, you need 5. Q is for dividend. Here I put it for 0%, so no dividend. Now what you need is, let's say, let's take an example. So you have a stock of $100, a strike of $100. So in this case, we call this at the money option. And say we have a 3% interest rate. The annualized volatility of the stock is 20%. And we're looking at a 3-month maturity here, 0.25, a quarter of a year. Now, you can just put in the formula for D1. So you'll be able to calculate what D1 is, D2 is. And then Excel allows you to calculate the N function. So you have ND1, ND2, N minus D1, N minus D2. So you will get those value as well. So you have those values. Then put in the formula of a call. So you will get the call price and the put price. So that basically tells you what the derivative asset of a call or a put will have their price based on the Black-Scholes Merton formulation. Now you can check that the put call parity actually exists. If it's a validation check here. So there's the put call parity, C plus K times e to the power minus RT should equal to P plus S naught. So you'll find that they are equal, so they check out. Now, with the Black-Scholes Merton formula, we have to take a look at, yeah, it sounded right. We have gone through a risk-free a process to derive the risk-free portfolio, and then we derive this partial differential equation. We said we solved it, and we reached that formula. Now, does the formula make sense, right? Does it behave in a way that we would expect? So we can actually go through a few sanity checks to ensure that, or to convince ourselves that the formula actually make sense or produce value that we expect to have. So we can check a few conditions. There are more, but let's just check 3 here. So we have a condition where what would the price be for a call and a put if, let's say, the underlying stock price is going very high, going to infinity, right? So in that case, usually if it's a call, you will for sure be exercised. If it's a put, you probably wouldn't have any value. So what would happen if the stock price were to go down to 0? So basically, the company is bankrupt. And what if the volatility, or in this case, the variance, is go to 0? So the price is not going to move anywhere. It just gets stuck to the current price, right? And we sort of numerically shown that the formula does demonstrate the put-call parity. So which is actually a good thing for us, convince us a little bit that the formula makes sense. Okay, so if, as mentioned earlier, if the initial stock price were to go to infinity, basically in this case, there's no chance that the call would not be exercised. Okay, so in this case, the behavior of the call is very much just like the behavior of a forward contract with a delivery price K. So what you have is whatever this value minus the present value of the delivery price will be the call value, the current call value, because that's what the price of the a forward contract at present time will be. And if the price were to go to approach infinity, that call essentially would just be like a forward contract. So you should have that forward contract price. So let's see whether that's the case or not. As mentioned, that you would expect the put will be 0, because no matter how high the strike price you will have, the stock price is higher than that particular price, so you would not exercise. So the put will be worth nothing. Now, if the initial stock price were to approach 0, basically the company is approaching bankruptcy. So in this case, the call will have no value because the stock price is never greater than any non-zero strike price. Okay, but the put will for sure have a value, the present value of K, because at maturity you will for sure receive K, and right now is then the present value of K. If the stock price were to stuck with volatility 0, basically it's not going to change, becomes a constant. Okay, so the stock then is a risk-free investment because it doesn't change. And so then if the stock current stock price is greater than the strike price, you will have a constant value, the value being the stock price value minus the present value of the strike, right? So if the stock price was lower than this here, than the present value of the strike, you will have 0 because the stock price is not moving anywhere. There's no any chance that this value, if this is lower than that, it will ever be greater than that. So it's not possible. So your call price will be 0. Now, the situation for a put will be totally opposite. If the stock price were to be lower than the present value of the strike, then whatever that value is, that's the price of the put. Okay. If the stock price were to be greater than this, then the put will be 0 because there's no chance you're gonna be able to exercise. So in the next one, we're gonna see, from the formula, how this thing actually materialize.